I'm Andy Clem.
I'm Zach Grove.
And I'm James Reese, and we're Embedded Systems Fall 2014 Team 4.
So in this project, we had to have a rover, and we were in an unknown room, an unknown location, and we had to get to a destination that we were given using a map that we were also given.
So the rover was to drive around the environment and build a bit of a map and use that to determine its location. After finding its location in the provided map, plot a course from its current location to the target location.
And the other requirement was that the rover was intended to act independently of the base station that would be powering it or be sending it commands. So all the commands were generated and all the processing was done on an off-board arm. In the end, we ended up using a laptop for this purpose instead.
Here's the general overview of our rover. The actual rover is outlined within the green box. Here's our master PIC. It communicates with the motor PIC and the sensor PIC over I2C. The sensor PIC takes the information from sensors 0, 4, and 5, encapsulates that with their own message format, and adds a sequence number, and sends it to the master PIC. The motor PIC handles the motor encoders here and here, sends that information back to the master PIC. The master PIC takes the information from the sensors and sends that over to UART to the Wi-Fi. And the other Wi-Fi down here, connected to the laptop, is what controls our algorithm. It checks the sequence bits and the checksum to see if we have any drop messages, and handles the algorithm stuff right there.
So the message format consists of a few fields. It begins with 2 start bits. The start bits are set to 1, 0. And it comes with an empty flag, which is used internally on the rover to determine if one of the sensor cues does not have any values in it. It is used for preventing any errors on the rover. The next field is 5 bits of sequence data. This is just a value that counts up with every value or every message that is sent, so we can tell when a message has been dropped or lost. There are 16 bits of data. The data, when it's coming from the rover to the laptop, will consist of a formatted value of the sensor, which is measured in centimeters. And if it's a message going back to the rover, it consists of a few different fields. So if we're going to send a motor command to the rover from the algorithms, we instead put in 2 bits of an operator, which is either going to be defining that it should move forward, in reverse, or rotate clockwise or rotate counterclockwise. It'll have a flag. It will have a speed that is 3 bits. The speed will be just 0 to 15, how fast the rover should move or rotate. And it'll have an amount, which is a distance that the rover should drive or a degree angle that it should turn. When we get back to the main message format, after we put the data in it, it has a source. The source is the sensor that the value is coming from, so we can differentiate between the different values being returned from the sensors, or the motor code when we are sending a value to the motors. And then finally, and most importantly, it has a CRC bit, or CRC checksum, which is 4 bits. So the CRC checksum actually gets us a lot of things, both internally and externally. So CRC is a checksum that is calculated off of all the bits in the message, and we are able to check the CRC to see if the message format is valid. So we can throw out any invalid messages internally on the rover if a message is bad or comes over incorrectly. And if when the messages are being sent to the laptop, or the laptop sends messages to the rover, the laptop and the rover will both check the CRC to see if it's receiving a valid message. And if it isn't, it probably received a bad message or it dropped a byte, in which case it will try to realign to the bytes coming in over serial.
Alright, the purpose of the motor PIC is to interface over I2C with the motor controller to drive the rover. The message sent to the motor PIC includes a speed, a direction, and a distance for the rover to travel. In order to drive the rover the correct distance, motor encoders are used to trigger a stop command to the motor controller itself after the correct distance and travel on the wheels. In order to avoid missing motor commands and so that the control program will know when motor commands are finished. An acknowledge message is sent after any motor command is received, and when a motor command is completed, a stop message is sent.
So in our design, we were trying to choose between two different types of sensors, one ultrasonic and the other infrared. We finally decided to go with infrared, mainly because ultrasonic, as you can see here, has a very large beam versus infrared's narrow beam. And really couldn't tell whether an object would be here or here versus infrared, where the object's basically in front of it, it can tell. Also, ultrasonic has more potential for interference. So we decided to go with infrared. So the way that infrared sensors work is that it sends a beam of light out until it hits an object and it returns, and depending on the amount of time that it takes, it gets a certain value. But because it is an analog sensor, we're looking for a distance value to print out. So in order to figure that out, we use an A to D, analog to digital module. And this is the way that it works. Basically, we have a high voltage reference value and a low one, and that's all over 1024. And each one of these, it's 1024 because each one of these is a tick, so 1 through 1024. We use 3.3 volts as the high voltage reference because that is what the PIC is sending out. And we use 0 volts as the low. So with this formula, we get each little tick being 3.22 millivolts. And we take this value and use a formula that we find by taking the infrared sensor and plotting the different values and the different voltages that it prints out. And then depending on that, you plot it on Excel and find that formula.
So this is the main algorithm the rover will follow to navigate its way around the map and figure out where it is. The rover begins in an arbitrary location, and it will start by spinning to figure out where it is. And once it spins and finds the nearest wall, it will begin to follow the first wall. It'll follow each wall until it hits a wall in front of it, or not hits it, but senses a wall in front of it. It'll stop then and rotate 90 degrees and continue to follow the next wall. It'll continue to follow walls all the way around until its map alignment algorithm figures out where it is. So with each wall that it begins to follow, it'll start to sum up distances in centimeters as it goes along. So it would figure out the length of the wall as it goes, and then at the end of the wall, it'll compare the length of that wall and the length of all walls that it has found so far against a list of the lengths of all the walls in the real map. It'll just do a linear search through all the walls until it can figure out where it is. So the way that the rover actually follows the wall is by following this finite state machine. Once it's precisely aligned to the wall, it'll begin to move forward in 40 centimeter increments. Every 40 centimeters, it'll stop and try and calculate what it should do next. So its next moves after it, at any point after it makes a movement, is either to continue moving forward 40 centimeters at a time if there's no obstructions at the time or in front of it. It'll continue to move forward and continue to add to the total length of the wall. If there's an obstruction in front of the rover, less than 40 centimeters on the front sensor, then one of two things happens. Either it's the end of the algorithm and we can figure out where we are, or it's the end of a wall and we need to follow another wall. So it will attempt to do a map alignment to figure out where it is. If it succeeds, then it's done. If it fails, then it will rotate 90 degrees and proceed with the exact same wall following algorithm as it has been. And it'll calculate its next move. If it gets to calculating its next move and the left sensor is maxed out, either one of the two left sensors is maxed out, that means that the left wall's disappeared and needs to make a left turn. So it will align to the wall again, drive forward, and then proceed with the left turn. If it needs to calculate its next move, and either one of the left sensors is reading either less than or greater than 2 centimeters difference than the other left sensor, or either the left sensors is too far from the wall or too close to the wall, it will adjust its angle of approach in 3-degree increments and then proceed to drive further to get closer or farther to the wall that it needs to. And it'll continue to do that until it figures out where it is on the map. To test our algorithms, we found it useful to have a simulation. The sensor values are sent out over a serial device, just as the real rover does, and then the algorithms accept those messages over another serial device, which could be running on a separate computer, and then executes the finite state machine and sends back motor commands. So I will now run the the algorithms. Begins by turning to find the nearest wall, and then it will rotate backwards to align to that wall. Once it aligns to the wall, it will continue forward until there's less than 40 centimeters in front of it, and then it'll turn and follow a new wall. Every new wall that it follows, it calculates the distance of the wall as it moves by the distance that the rover has moved, plus the front sensor value, plus the size of the rover. And then it'll continue until it has followed enough walls to determine that it is at the end of the wall that it knows. In this instance, it follows the first two walls and realizes that those two walls could still be these two down here. So it'll follow one more, and at that point it knows there's only one possible location, one possible wall that it could be aligned to at that point. It'll stop.
Alright, there were some discrepancies between the actual rover and the simulation. Most notably, at certain speeds and distances, the actual travel distance was not as close to the expected travel distance as we would like. However, with some tuning, we got it close enough that we could get accurate driving. The sensors also posed a problem when all were connected. With our one battery, we could not source enough current to power them all fully, and we would get erroneous readings. However, when we removed the two unused sensors, all sensors could be powered fully, and we no longer had that issue. With regards to the algorithm, in order to ensure that everything works well, when a command is sent to the rover, it is resent until it receives acknowledge from the motor pick, and when waits for the stop message from the motor pick before it moves on. On the algorithm, however, often the movement complete messages were missed. They appeared to arrive at the control computer, however, were not recognized within the program. However, despite this, the message format is quite reliable and supports detection of errors both over the I2C and the dropped bytes that may occur over UART, and easily allows us to refine the message position and stream of bytes.
So for the integration of the rover, everything went fairly well, although we did have to make a lot of minor tweaks between the algorithm and the rover itself to get everything to work together well. For instance, for the algorithms, initially they used very small movements forward and backwards and very small rotations in either direction, which caused some twitching motions over the rover to sort of stall out or slip in a lot of cases. So we used larger rotations and larger movements to get over that issue.
When interfacing the master pick with the sensor pick, which had not previously been connected very much, the sensor pick was found to hang the I2C bus every now and then, which would cause basically unrecoverable failure on the rover. So that was, however, fixed, and I2C communication went smoothly from then forth.
Another issue that we had was on the short-range sensor or mid-range sensors. We were having issues, and so we just changed those out with some other long-range sensors that we had, and we scaled down the amount of sensors we had from 5 to 3. And so after encapsulating the data within the message format, the messages transferred successfully throughout the entire system.